So in this talk, I'm going to present some observations of the BGP behavior under one stressful condition. And I'm also going to present an analysis of what contributed to the observed behavior. This project is a joint effort between UCLA, ISI, ILJ, and UC Davis. You can download our full paper from our project website. The URL is on the slide. So, first of all, we're interested in understanding how BGP performed during the Nimda worm attack in September 2001. I'm showing a plot of the hourly BGP update count received at the monitoring point RLC0 at RIPE NCC. As you can see, on September 18th, 2001, between 12 p.m. and 1 p.m., the monitoring point received 50,000 BGP updates, but 2 hours later, they received about 1.5 million BGP updates in an hour. So this represents a 30-fold increase in the number of BGP updates received by the monitoring point. This evidence has been used by other researchers to indicate that global routing instability occurred during the worm attack. If you attended the NANOC meeting 1 year ago, you may still remember that the Renesas Corporation presented this finding in their talk. So in our work, we want to understand exactly what are the causes of the spike. And we want to find out whether this kind of spikes really indicate routing instability in the global internet. First of all, the spike could have been caused by the worm. As one report from the Science Institute says, the Nimda activity started at about 1 p.m. On September 18th, 2001, and proceeded to taper off in the following hours. It seems that the activity of the worm correlates to the big spike in BGP update very well. However, this kind of spikes has also been observed before. It could be caused by implementation bugs or protocol design problems. It could also have been caused by BGP misconfigurations, or we may find other causes. So what we did is to re-examine the data used by the previous researchers. What we did is to use the BGP update messages collected by the monitoring point RRC00 at RIPE NCC from September 10th, 2001 to September 30th, 2001. This monitoring point has 12 BGP peers. It has 3 US peers. They're AT&T, Vario, and Global Crossing. It also has 8 peers in Europe and 1 peer in Japan. So with this diverse set of peers, we should have a good picture of what exactly happened in the different ISPs during the worm attack. So in order to identify what caused the spike, we first classify BGP update messages and then identify the causes of each class. We first classify the updates into announcements and withdrawals, and the announcements are further divided into new announcements, duplicate, and implicit withdrawals. We further divide the new announcements into BGP table exchanges and 3 other categories. For implicit withdrawals, we know that each route can be composed of several BGP attributes. There are the AS path attributes, NAT, and community attributes. So if the implicit withdrawal doesn't change the AS path attribute, then we call it an S path implicit withdrawal. If it does change the AS path, we call it a D path implicit withdrawal. We give an example of how we classify the BGP updates. First, let's suppose that at time t0, there is a session reset between the monitoring point and the peer router. Then at time t1, we receive an announcement for the prefix 216 and 200.16.216.0. Since this is the first update for this prefix, after the session reset, we call it a BGP table exchange. And then we receive a withdrawal for this prefix. After the withdrawal, we received a new announcement for this prefix. And we can see that the AS path in this announcement is different from that announced at time t1. So we call it a new announcement with different attribute. It's called nada. Otherwise, we call it a flap. So at time t4, we receive another announcement for this prefix. And we can see that all the attributes, the AS path and the community attributes, are exactly the same as the route announced at time t3. So we call it a duplicate. At time t5, we received an implicit withdrawal. You can see that this, the AS path part is different from the AS path part announced at time t4. So this means we get a new AS path to this prefix. So we call it a D-path implicit withdrawal. At time t6, we got another implicit withdrawal. However, the AS path part remains the same, but the community attribute is changed. So we call it an S path implicit withdrawal. So using this classification method, we plotted the number of BGP update messages we received every day from September 10th to September 30th. The red curve in this graph shows the total, and the green curve shows the number of announcements, and the blue curve shows the number of withdrawals. We can see that September 18th, the warm attack day, received the highest amount of BGP update. And September 30th received the lowest amount. And one more observation we can make is that most of the BGP updates are announcements. About 87.3% of the total updates are announcements. And this number is even higher on September 18th, where there were about 91% of updates that are announcements. So the withdrawals are indeed a very small portion of the BGP updates. Then we further classify the announcements into 5 categories. In this graph, we show that how many BGP table exchanges we have on each day, how many implicit withdrawals we have on each day. So we can see that the implicit withdrawals are usually the largest component. However, on September 18th, the largest component is the BGP table exchanges. And this category varies a lot. Sometimes it's the second largest component, and there were 0 table exchanges on 9 of the 21 days. So let's take a more detailed look of the warm attack day. So we break down the BGP updates on this day into 5 large categories. On the right, we can see that the largest component is the BGP table exchanges. About 40.2% of all the BGP updates are BGP table exchanges, and 5% of the BGP updates are duplicates. This is very surprising because none of these two categories represent real routing changes in the internet. So we want to know what exactly caused these two types of BGP updates. And on the left of this pie chart, we see that there are three categories. One is the new announcements. This doesn't include the BGP table exchanges. And the second part is the implicit withdrawals. And the third part is withdrawals. We can see that the largest component in the real routing changes are the implicit withdrawals. It represents about 38% of all the BGP updates. So we want to know what caused the implicit withdrawals. Now we look at the 2.7 million BGP table exchanges on September 18th. We found that they're caused by 30 session resets between the monitoring point and the peer routers. In the figure on this slide, we show that exactly when those BGP session resets occurred. Each mark on this graph represents a session reset. The x-axis is time and y-axis represent different peers. So first we can see that all the session resets on September 18th occurred between 2:20 p.m. and 4:40 p.m. This is when the RAIN attack was the most serious. And the second observation we can make is that there is very obvious synchronization between the session resets. So in order to understand what caused the session resets, we trace the routes from the monitoring point to the peer routers using the tools provided by RIPE. We can see that all the routes to the peer routers share the same first two hop routers. And in fact, the second hop router is actually one of the 12 peers of the monitoring point. We can see that whenever the second hop router, R2, has a session reset with the monitoring point, all the other sessions would break. So this suggests that there were some serious problems near the monitoring point, and this caused the synchronization between the session resets of all the different sessions. One more point I want to make with using this graph is that the monitoring point is peering with the peer routers using multi-hop sessions, and we know that almost all the operational BGP peerings are direct peerings. So in general, the multi-hop BGP sessions are more unstable than the direct peerings because they are subject to the congestion and routing problems at each of the hops. So one conclusion we can make from this is that the monitoring process was obstructed by the worm, but we cannot claim that the same thing occurred in the operational internet. And now we remove all the BGP table exchanges because they're monitoring artifacts. So we see a somewhat different picture. The lowest point on September 18th is still 15,000 BGP updates. However, the highest point becomes only 0.3 million. It was originally 1.5 million before we removed the BGP table exchanges. And now the highest point becomes 0.5 million between 3 p.m. and 4 p.m. on September 18th. One more interesting point in this graph is that the highest spike is actually on September 25th. There were about 1.1 million BGP updates, received between 6 a.m. and 7 a.m. on that day. So what this tells us is that the monitoring artifacts are very misleading. So if we don't remove those monitoring artifacts, then we cannot reveal the real problem. And also that the BGP instability on September 18th is not the most obvious, is not the most serious. Then we look at the duplicate announcements. They make up about 4% to 10% of all the BGP updates. However, they represent about 31% of all the BGP updates from AT&T. We talked to AT&T and we found that this is most likely an implementation problem. They're triggered by changes to non-transitive attributes. So for example, if the BGP route to a certain prefix changes and the part that changes in that route is a next hop attribute. And when the router that receives this announcement redistribute this route to an external BGP peer, it's going to remove the next hop attribute. And the remaining BGP update is going to be exactly the same. So basically the problem is that R2 in this graph doesn't check whether the change is to a non-transitive attribute or to a transitive attribute. So what we learn from this is that there is some saving in the implementation by doing this, but it increases the overall system overhead because all the neighbors of R2 has to process these duplicate announcements. Okay, so after understanding what caused those BGP table exchanges and the duplicate announcements, we now move on to the updates that represent real routing changes. First of all, we found that among all the implicit withdrawals, there are about 22% that don't have changes to the AS path. So in other words, the AS path part remains the same, but the other attributes such as the MED and community attribute changed. We have a graph showing what's the percentage of implicit withdrawals that are S path for the 3 US peers. We can see that AT&T is down at the bottom, the red curve. So it shows that less than 10% of the implicit withdrawals from AT&T are S path. However, about 40% and 70% of the BGP updates from Vario and Global Crossing are S-path implicit withdrawals. We don't understand exactly what caused this kind of difference, but we know that if an ISP changes its MED or community attributes very frequently, then its neighbor may have to alternate between several different exit points very frequently too, because those MEDs or community attributes are used mainly to promote or decrease the preference of a certain route. So in other words, the neighbors, when they receive the S-path changes, they will have to choose another exit point to the same peer, to the same neighbor. So we would like to understand what exactly caused this kind of changes, this kind of difference. After we remove all the table exchanges and duplicate announcements and S-path changes, we see that the lowest point on September 18th becomes 40,000, and the highest point on September 18th becomes 0.2 million, and the highest point now is 0.4 million. The highest spike on this graph is still on September 25th. Now we want to know, among the BGP updates that represent real AS level topology changes, exactly how many prefixes had, for example, 10 routing changes, how many prefixes had only one routing changes, and there may be some prefixes that didn't have any routing changes at all. So we plotted the distribution for every peer on every day from September 10th to September 30th. On this graph, what we're showing is AT&T's distribution on September 18th. First of all, we can see that there is a group of prefixes that contributed to the total disproportionately. So if we look at the last bin, the rightmost bin on the graph, all the prefixes in that bin had 10 or more routing changes, and there are about 2,500 prefixes in this bin. However, they represent more than 60% of all the implicit withdrawals. So this means a small group of prefixes actually contributed to the majority of the real routing changes. This observation is common among all the peers and on all the days. The second observation we can make from this graph is that if we sum up all the bins, we know how many prefixes had at least one route change. And we see that only about 14.4% of the prefixes in AT&T's routing table had one d-path change. So in other words, 86% of the prefixes didn't have any d-path changes. So in other words, we cannot say all the prefixes were unstable during the worm attack. We did observe some spikes in the d-path routing changes. For example, we show that SurfNet experienced a spike around 5 p.m. on September 18th. What we found out is that about 40,000 prefixes changed their path almost around the same time, and then the return to the original path shortly after the previous change. So this caused a big spike. One possible explanation of this phenomenon is that SurfNet, the operational session between SurfNet and one of its peers probably broke around this time, and the session came back shortly after the session broke. So all the routes that previously used that peer as the next hop has to change their path, and after a while they have to switch. They have to return to the original path when the session comes up. So this shows that if our explanation is correct, this shows that there were operational peering sessions that broke on the worm attack day. However, based on our observation that these spikes were not frequent, so we can probably say that the frequency of the session resets of the operational sessions was not as high as those between the monitoring point and those peer routers. So now let me conclude the presentation. So first of all, we found that excessive session resets at the monitoring point contributed most to the spike. This is a monitoring artifact. If we are not careful when we are looking at the data, then we may arrive at the wrong conclusion. The second conclusion is that a substantial amount of BGP updates don't reflect AS level topology changes. For example, the duplicate announcements and those S-path implicit withdrawals. Finally, we can conclude that there were a small group of networks that are probably seriously affected by the worm attack, and BGP allowed those local changes or local unreachability to propagate to the whole internet. And this is why we saw that the majority of the routing changes were contributed to by those small group of networks. So there are mainly 3 or 4 related studies. Leibovitz and other people studied BGP pathologies before, and actually our study also found some of the previously identified problems. They still exist in the internet. For example, the duplicate updates. The second and the third related study is about the BGP behavior under congestion. And both of these 2 studies showed that when they experimentally increase the network congestion level, BGP sessions will break. Our empirical observations seem to support their conclusion. And the fourth related study is by Manel and Feldman. They analyzed BGP traffic characteristics to produce realistic BGP traces. They also identified some characteristics that we see in this study. However, their main purpose is to produce BGP traces in test lab environment. Our main purpose is to diagnose problems in the BGP traces. This is a list of references. So this is the end of my talk.
So, can I just postulate one thing, and that is in the event of something like Nimda rolling out, you may not have actually been observing the BGP session dropping from congestion per se, but it may have been an overly active engineer at a particular ISP or a set of ISPs going, oh my God, I've got this whole bunch of traffic going through, I don't recognize it, are they flooding us, are they attacking us? Let's tear down the session and see what happens. Oh, the traffic came in another way, let's bring it back up.
Yeah, that's also one possible scenario. Yeah, it could be congestion or router reboots.
But
yeah.
I'm actually postulating that in a lot of these cases, it's the humans that inject the instability, that the routing protocols, if left alone, may actually weather the storm better than if we as engineers start getting involved and poking our fingers at things to maybe try to make it better.
That's right.
Just an observation.
We went back to the operators of a sampling of the sessions that were reset. That was the only session reset on the routers, and it was not done by hand. Realize also that even if they'd gone to reset sessions, they wouldn't have chosen to reset this one because this is a multi-hop EGP peering to a research peer where no routes are really being received. So it's uninteresting for ops to reset it, though of course if you are silly enough to allow fingers on your routers instead of configuring things automatically, anything can happen.
Yeah, just minor comment. So you focused on the spike, but it's not about the spikes really. I mean, if you looked at the withdrawals after cleaning up the data, the interesting thing is the sustained level of withdrawals. It's about a factor of 5 or so higher than normal, going for about 24 hours. And I think it's quite feasible that it may be several thousand networks. There's no more really involved. Another thing that's interesting is I don't think you looked at code red at the same time. Now, code red does not have any artifacts related to session resets. And it has a pretty similar general behavior, too. So I think that where digging in is not sort of, to filter out what you call S-paths, meaning updates that do not change AS-path attributes, but to ask deeper what exactly caused it. And why do you have so significantly higher level of updates that reflect internal changes in ASs rather than external BGP paths? So I think we still don't have a clear-cut answer what exactly has been going on.
Yes.
And I want to stress that the spikes don't matter here. Let's not confuse, the tree for the entire forest.
Yeah, you're looking at one subset of the BGP updates, that's the withdrawals, right? You're saying there's increase in the withdrawals. And
quite considerably, yeah.
Yeah, we don't contest that there's increased BGP routing instability, but we want to know whether the instability occurred all over the internet, or are they contributed by a small set of the networks or not?
Yeah, I agree. It's several thousand networks, yeah.
Yeah. And one more clarification I want to make is that although this worm didn't cause widespread damage to the BGP routing protocol, the next worm may do. So we're not saying that we shouldn't be concerned about BGP problems. In fact, one of the reasons we look at this problem is trying to identify what are the weaknesses in BGP that we have to improve or fix in order for the protocol to be more resilient to the next worm attack. So as we have heard in the previous talk by Worm Paxson, there could be a much more powerful worm. So when that worm comes, we want to know whether BGP is ready or not. So there's one aspect of this study that's to identify the BGP weaknesses. I'm not emphasizing that aspect a lot in this talk, but you can find it in our full paper. So thank you.